Okay, so one of the exercises basically asks you to do something that's very much related to this picture. And this picture is just, again, your same dimensioned matrix. And we apply it for 3 steps. And we know what the eigenvector is because we worked that out. And at least we can verify that that's an eigenvector, because what's an eigenvector? It's a vector you multiply by the matrix and get another vector parallel to it in the same line. Eigenvector means you apply the matrix and it's along the same line. Okay, so you might want to review the videos from yesterday to make sure you understand that. And I might write a clarification for you at some point. You know, there's more to do than I can possibly do in the time I have, okay? Even if I spend 24 hours a day at it. And of course, if I spent 24 hours a day at it, I wouldn't be sleeping and you would end up with garbage, okay? So, spending most of my time on this, okay? Once in a while I eat and once in a while I sleep. Okay, so, so I'm going to do as much as possible, but I've also got to come up with, you know, exam problems and all that stuff, okay? So, it's just all part of the process. So, I'll give you as much clarification as possible, but then a lot of times the clarification is going to be, work this out and do it right. Here's one step, work this out, and I'll go back and revisit what you did, okay? So, in any case, this is your eigenvalue, and if, I'll kind of rewrite this picture. I'm going to point my finger. So this is an eigenvector. If you transform the matrix, if you use a matrix to transform this vector, if you multiply the matrix by this vector, this is what you're going to get. Okay? It's a stochastic matrix. So the vector has to, you know, the components of the vector have to add up to the same thing every time, and they have to be along the same line, so you're going to get the same vector, meaning your eigenvalue is 1. Now you do the eigenvalue equations, and most of you, wrote those down. If you solve those correctly, thing factors, I don't have the details here, but you factor into lambda minus 0.7, sorry, it's lambda minus 0.7, lambda minus 1, right? So your eigenvalues, your lambda values, are 1 and 0.7, because of course that factor thing equals 0 and all that. Okay, and again, details were yesterday. Just reminding you of where it comes from, right? And reinforcing what it means. The eigenvector is a vector that when you multiply it by the matrix, or transform it, because that's what I mean, okay, gives you a vector on the same line. Maybe in the same direction, maybe in the opposite direction. In the case of this eigenvector for the basic same dimensioned problem, it'll be the same vector. So if you multiply this matrix by this vector, you get this vector. Okay. Now the other eigenvalue was 0.7. You see that here, lambda equals 0.7. And if you work it out, the components of that vector are identical, except one's negative and one's positive. Now at least I saw one paper, I forget where it was, who absolutely got that. They got x equals negative y, and then didn't quite write down the eigenvector right. Well, at that point, you're not going to see it, but all you had to do is go back and do that one little step, very simple step, correctly, and you'd have had it, okay? So I'm seeing a lot of that, okay? Seeing a lot of stuff where there's one little step that could easily be done correctly that wasn't, and it throws things off a little bit. So you want to be able to do that carefully. I'm seeing people writing the right equations and doing most of the right stuff, so you're in pretty good shape with that. It's the first time you've seen it. So you're really doing pretty well, as you've always been. Okay, so anyhow, there's your eigenvalue, and your eigenvector, I said, is like negative x. Okay? And that would be like, could be negative 1, 1, or 1, negative 1. any multiple of negative x could be your eigenvector, okay? But what it says is your first component is equal and opposite to your second component. So if this one's negative, this one's positive, right? And if you did the other way, it could be 1, -1, it could be here, but it's still going to be on the same line. Now, the big deal. Two big deals. First of all, you see this sequence 50, 35, 24.5. Okay? You used that sequence in your homework to do an exponential model, right? And at least some of you got the exponential model. Maybe you used 50 and 35 with your a, b to the x, and you got your a and b, and you got your model, and then you plugged in 24.5 or 3, and you got 24.5 or something like that. Okay? So at least a couple people got all the way to that. So, that's pretty good if you did. But it's a pretty simple process if you know how to do that a, b to the x and solve for a and b. Okay? That's something that, I'll try to clarify in the way I state some of the problems. The other thing is, I ask you to find the slopes between the tips of these vectors. Okay? You know what the slopes are between the tips of these vectors? Anybody get a result that's memorable? Well, from the tip of this vector to the tip of this vector, the slope is -1. From the tip of this vector to the tip of this vector, the slope is -1, meaning that these vectors lie along a straight line. Now they should, because for this model, your sane plus diminutive always adds up to 1,000, doesn't it?
Yeah.
So if s plus d is 1,000, then d is 1,000 minus s. That's the equation of a straight line with a slope of -1. If it's y equals 1,000 minus x, you know that's a straight line with y-intercept 1,000 and slope -1. If you know straight lines. And everybody should know straight lines, forever for the rest of their life after Algebra 1, but everything's done by formulas, so you forget formulas and haven't sorted out meanings. So, maybe it's a little unfamiliar. It doesn't come out to you. And I'll admit, last year, and you can look at the videos, I thought that line would curve a little bit because I wasn't thinking. And I said, okay, let's see what the curvature of this line is. Let's do a curve fit or something like that, and found out it was a straight line, and then I went, oh, duh. Okay? It's clearly a straight line if s plus d always adds up to 1,000.
So that's what you meant by each vector would be on the same line?
Yeah, and they're all on the same line, and that's the line. The tips of the vectors are all on the line with intercepts at 1,000. Straight line from 1,000 here to 1,000 here.
Can you have an eigenvector with rational or irrational?
You have that. I'm not going to talk about it right now, but it's, I gave you a little note on it. And I just said, you work it out with the irrational numbers, or you do a decimal approximation to maybe 4 places. And then you're close, but not exact. Since you can't express an irrational number exactly, you're kind of stuck with that anyway. It's a good thing to work it through with all the radicals and stuff. And you can do that. Just got to keep your wits about you, and algebra has to be up to it. Okay? Anyhow, that's what we've got. So that picture is really important because what it tells you is the slope of this line is the same as the slope of this, which means that you could express every one of these vectors here as this eigenvector plus a multiple of this eigenvector. And that explains why this is exponential. So that's a really important picture. So let me draw it. So the basic sane diminutive model, or the standard sane diminutive model, which I take to be 1,000 people and transitions of 10 and 20% in. Okay? first of all, where is, oh my goodness, let me try to use one of these. I think maybe if you pump this thing a little bit, then it works better. Okay? So I'm going to draw, and these things clean up really nicely. This is your eigenvector. .666 2/3. Try to get that 3 in there and not smudge it too badly. 333 1/3. Its eigenvalue is 1. And then, so far that worked fairly well. Let's go with green and see how it does.
How do you know what the eigenvalue is?
Huh?
How do you know what the eigenvalue is?
You do what we did yesterday. Solve for that lambda. And then you plug that in, you get two simultaneous equations, they turn out to be the same. So you really have to write it out. And the algebra is a little bit demanding. But anybody with an Algebra 1 document background can understand it and do it. Okay?
Mm-hmm.
Now the more algebra you've done, the easier it is to do. But it's just straightforward algebra. But maybe a little bit unfamiliar. Like remember when we solved for the y over x, solved each equation for y over x, and then set those equal? That's where the quadratic equation came from that you solve for lambda. And if you do it with your percents, it's probably not going to factor into nice numbers, like 0.7 and 1, okay? You're going to get something that might well be irrational, probably will be. And if it's irrational, you know, just blame your name because that's where the numbers came from. Change your name to something that'll give you nice numbers. Yeah, it have to be a legal change before you can use it here, so you probably don't have time to do that. Okay. Now, this is your eigenvector. Negative xx. Okay? It could be any multiple of negative 1, 1. Okay? Make sense? I mean, you know, you get this. Just what we did in class yesterday gives you this picture. Now I can make this vector as long or short as I want to. So I don't have to specify what its coordinates are. I just know its x and y components are equal but opposite in sign. So it's along this line here, just a big old line through here. Now, if you do the transitions, and let's see, these colors are working okay. Blue's a little hard to see, so I'm not going to use it. The one I've got out in the vehicle has a bunch of different colors instead of just 4. But I'm afraid the markers are going to be like the other ones where you can't easily wash them.
Well, you never know till you try.
They wash, but the board comes out looking kind of like this. So I'm going to have to clean those boards. And I'm sure I'll be able to clean them, but it's pretty easy to put another coat of black paint on them too, new chalkboard paint. So, you know, I'm not going to have a problem there. But I think if I wash that once more, most of that stuff would go away. But it leaves a bad residue, okay? So I hesitate to use them. I'll experiment with them later. Okay. Now, if you start from any population configuration, there's your starting population vector. Okay? Then, your next population vector will be, well, first of all, your starting population vector and your eigenvector form a straight line. Okay, now I'm going to risk blue on that straight line. That's the color everybody wanted me to use earlier. But hopefully it'll be visible. If it isn't, I'll write over it with something. Okay, so the straight line is going to be here. I'm not sure how straight that line is.
What's that word before vector? It says starting what vector?
Starting population vector. It's a population vector. For the same dimensioned model, these are populations. Like here's a population vector, and wherever you start, you're going to exponentially approach this one. And it's an exponential approach. You see how this model combines a lot of things that we've looked at over the last 8 days, okay?
What if we can't get a line that goes to the top of our vectors and meets the y and x?
Then you didn't plot them correctly, okay?
Yeah.
So you want to replot them a little more precisely. When I say you didn't plot them correctly, you didn't plot them precisely enough. There will be a line, and that line will go through, it'll be the line that goes through 1,000, 0, and 0, 1,000. Okay? Okay, well, now, what turns out in this case is the tip of this vector gets closer to the tip of this vector. Okay? And let me put one more thing down here. The eigenvalue for this eigenvector is 0.7. Okay? Now, you do your population. If this was the 500, 500 vector, you would end up with 550, 450, right? And everybody should be real familiar with those numbers because we've used them a lot. But it depends on how well you focus on numbers. Okay? And if numbers to you are mostly just things that your calculator gives you, you won't be as focused on them as if you actually think about them, right? And a lot of times in your math courses, all you got to do is punch numbers into your calculator, not think about them, write down the answer, pretend you understand. Okay? And that gets you by an SOL, which means probably gets you by a lot of your math courses. And I keep reiterating that because you want to push a little deeper than that. Just kind of get in the habit of pushing a little deeper, at least thinking a little deeper than what you're asked to do. Whether you get a result or not, if you get in the habit of thinking a little deeper, eventually it'll take over your life and you won't have anything else to do, and you'll fade away. No, don't let it go that far. Keep it within reason. Don't become totally obsessed with it. But if you do, then you kind of know what your calling is, don't you? Okay? Okay. And if you're going to be an engineer, you want to think more deeply, but you don't want it to take over. Not the math part. The engineering part, sure. Okay? If the math part takes over, it means you probably ought to go into math. But then you got to ask yourself, just how smart am I? And how hard am I willing to work, right? Because you got to make career decisions. And sometimes engineering would still be better career decision, or even another field. Okay, well, anyhow, that's digression. Okay, starting population vector. Now, the big deal here is that this vector is going to be about here. Okay? This is your next population vector. Here. And the tip is 0.7 times as far this thing's just not. Point 7 times as far from the tip of the eigenvector as the tip of the original vector. So what I'm saying is, this distance is 70% of this distance. And it has to be 70%. You know why? Because this eigenvalue is 0.7. Now there's a pretty deep connection there. And if you get a decent linear algebra course, which is typically like in an engineering curriculum at Tech, I think in the second semester of your freshman year, okay? Maybe the first semester of your sophomore year. We do it in the first semester of the freshman year, but we're going to change that. Okay, it's too early. People don't learn it as well as they could, or they have to work a lot harder to learn it than they would if they had some calculus, a little more mathematical sophistication. Anyhow, within the first 2 years of any mathematics-based curriculum, in any of the basically hard sciences, hard meaning something you can grab a hold of, as opposed to squishy things like biology, which is way too complicated. You get a linear algebra course. So you can pull this together, and it would be worth your while to review this when you take a linear algebra course. Understand this much, which will give you a good head start. And then, as you go through the course, look at it every once in a while until you say, aha, now I understand it. Because if you do, you got a pretty good grasp of, you're doing pretty well with linear algebra. Okay, so anyhow, the point again is, since the eigenvalue is 0.7, this is 70% closer to this. I mean, this is 70% of this distance, and it will always be the same for every subsequent vector. Okay? So let me finish my sentence. Come on, give me some ink here. Okay? Does that statement make sense in terms of what I just said? Well, now you can estimate what these vectors are going to look like. And you can compare your picture when you drew these things with this picture. Okay? So now you're going to go 70% closer than this, right? So this is going to continue. 70% closer than this, I estimate, is here. It's going to be, this distance here is going to be less than this distance here because it's basically 30% of a smaller distance. And incidentally, this is the way the orange juice acts too, with every sip. So then we go 30% closer, 30% of this distance, so we're at 70% of the distance, and we get this vector, right? And then 30% of this distance is about here, and 30% of this distance is about here. 30% of this distance puts you about here. 30% of this distance, 30% closer. Okay, and the 30% of whatever your distance is keeps getting smaller and smaller. Now, I'm not going to attempt to draw the rest of these vectors, but they'll be at these points, or points that look like this. So you're going to have an infinite sequence of points here, each going 30% closer to this one.
Wait, I
Also-
thought we were doing 70%. Where did we get to 30?
Well, if you go 70% of the distance, then you're 30% closer, right?
So then wouldn't it keep going down, or why do we stop and keep repeating 30% of each one? 'Cause I thought we were
Because
gonna
if we
repeat
go
70%.
30% of the distance, we're at 70%. Okay, like here I am standing here. There's a table, right? Now, if I want to go to 70% of that distance, there are two ways to do it.
Get to 70% from where
I
you
could
are.
calculate 70% of that distance and go to that point, right? Or I could calculate 30% of that distance and go that far,
Right. Okay, I get what you're saying.
right?
Yeah.
Okay, so yeah, you got to think these things through, because again, you haven't been taught to think the way people in countries with educational systems better than ours have been taught to think. And that's most countries, even third world countries, in many cases. Many third world countries are way ahead of us. Okay?
The math.
So, now when you talk about way ahead, and teaching people to think, yeah, pretty far ahead. Pretty far ahead. Okay. So, that picture is really important, and another part of the picture that's important, and I'm going to give up on these markers for now. It works better if you keep pumping them, but it's distracting. So, another way of looking at this vector now. So, let's just draw it again. Here's this eigenvector. And incidentally, one of your eigenvectors will always have eigenvalue 1. So if you don't get an eigenvalue of 1 out of your equations, you did something wrong. Okay? So you want to check that out. It says always has eigenvalue 1, whatever thing is, right? And you have, I guess I'll use color. You have this eigenvector. Okay? It's always in the form negative XX. Okay?
Is that a negative 0.1 beside that vector, or is that something else?
But the eigenvalue is not always 0.7. Okay? Now, you asked me about a negative 0.1 or something.
Right there it
You
says,
talked about this?
yeah, what is
You know,
that?
I honestly don't know what the heck that is, so it must be an arrow. Didn't want to make it look too much like a vector, but you understand this is the eigenvector, and this is just an arrow pointing to the eigenvector, telling you that that is the other eigenvector, right? Okay? So, you have this straight line, which is always, if S plus D is constant, you won't always necessarily have a total population of 1,000, right? And this problem doesn't just apply to sane people and demented people. That's an unrealistic model. Okay? That's one you kind of visualize. Okay? But whatever your total population, I'll say equal to the total population or whatever. Might not be population, right? And often it's probability, so it's just one. Okay? Then you can do this. You can say that this population vector here is the sum of your eigenvector and some multiple of this eigenvector. It's called the vector sum of and I didn't leave myself room to write my statement. And